That is hard. So I'll record it on my computer. I'm okay. Okay. You know where to find the files, right? So do I need to explain where to find the files or the lecture notes? Anyone knows where are the lecture notes, right? So there is one only page on the modules. Thank you, guys. Only one page on the modules that has all information that we need, including lecture notes, videos, worksheets, quizzes, exams. All you need to learn in this canvas is click on the modules, go that course schedule. So then you'll find everything. So for now, as I said, I'll give you a short introduction of the course, overview of the topics, and then we'll start our chapter 2, which for most of us, it should be kind of review. If we've seen what the logic is, maybe in different ways, maybe different words, maybe different level. So easier. I don't think here even is hard. It's just it's good. You can just remember from your high schools. So what's the discrete math? Discrete math for you guys is kind of, I will say, review the topics that you guys need for the programming. So when we are talking here about logic, number theory, and all of these fun stuff, for you guys means really how you need to use all of these topics when you are programming. So behind of all these math, abstract math topics is something that you in future, in really soon, you must use all of these topics in your programming, because this is a language that you need to talk to, in order to write your programs. And one more thing that's really interesting, maybe for you are you're not math major, you're just computer science or computer engineers, but all of these titles, all of these chapters is a major in PhD for math students. So it means I can have a PhD in logic, I can have a PhD in set theory, I can have a PhD in number theory. So that's how deep you can go in any of these topics. And we are really touching the topics as much as you need, and that's it. So we'll start with the logic. As I said, logic for most of us makes sense. We've seen it somewhere with the and or conditional statements. We just review for most of us, but some of us maybe not, haven't seen it, and that's the first time we see. And then set theory, I'm pretty sure we saw set theory in algebra classes, but the only thing is here, our set theory is based on the logic. So whatever we cover in the logic, we just somehow copy and paste and try to say the language in different way for the set theory. Relations, maybe not the way that we see relation here. We haven't seen it in any other courses. So whether it's equivalency or not, whether it's a partial order or not, in the way that we see relations in this course is completely different than the way that we define in calculus classes or algebra classes, because it depends on the reflexive, transitive, and that's one of, I would say, challenging for my engineering students. For proofs, as of now, for all of the calculus classes, all of algebra classes, you accepted the statements. I say, if a function is differentiable, so it's continuous, you won't have any problem, you don't need to prove it, you accept it. So this is probably the first place that we ask you to prove what you see. So if you see a theorem, if you see a statement, if you see a problem, actually we prove. In order to prove it, we need to know what's the methods for the proving. So the methods for the proving, it's brand new for most of us. And again, is another challenging topic because it's brand new. We haven't seen it before. But if we learn the logic behind of what we call it noun, what we call it unnoun, what do we call it assumption, what do we call it conclusion, hopefully we can just get the connection and find the proof. Induction, I think one of the powerful methods for proof is induction that you guys will need for any programming. So as long as you have any kind of loop in your programs, which most of us, we do have, the programs is repeating when we write. So induction is one of the powerful methods that you can just prove whether your loop works or not. And number theory, I think you guys know what is mod, remainder, like just this kind of expression that you have divide by 3 and write the remainders, and then you can just have the, I think, percentage notation for mod. That's what we call here number theory. Maybe not in the math version, but you've seen it in the computer science notations. Graph theory. So graph theory was part of 270B, recently moved to this course, which 270A, and it's, I think, one of the easy topics for you guys. But again, it's an easy one because you have circuits. So you've seen what's the circuits, you know how to make the connection between your just whatever Boolean algebra you have. So since you've seen that one, most of you guys, even though it's the last chapter, graph theory is the last chapter, but it's an easy one. You can get the full credit for that one because you have some background on that. So one more time, the good thing, maybe I don't know whether I call it advantage or disadvantage, but these chapters, each one individually is a major in PhD. So you can go deeply and just get a PhD in one of this one, and they are independent. So means you can be really great in number theory, maybe nothing to know about the logic, or maybe you are great in logic and set theory, you don't know anything about the graph theory. So the good, I don't know, I will call it the good thing. So if you get behind in one of the topics, it's fine because they are not related. Definitely they are not related. So they are independent chapter. That's what we're supposed to do. If anyone wants to add any question, comment, idea, what is Discord for this course? Somebody's looking for your Discord. I think last time, who made the Discord? Yeah, Kyle. Thank you. Okay. Anyone wants to add anything? No? Here we are. This is my first section of 2.1. So in order to start what we call logic theory, which are 6 sections, so it's a long chapter comparing to the others, we have to learn about the terminologies. I have to remind you some terminologies that you might seen before, but you don't remember right now. And that the first terminology or the block for what we call logic is propositions. So we start with the proposition. So proposition is like exactly the block for the logic, like the block for the building. So that is going to be the main terminology. So then after that block, we learn how to make the connection between the statements, which means you can have and, or, conditional, 6 types of connection between the statements, and then the true false statement or true false table that I'm pretty sure you guys seen somewhere, but maybe you don't remember, but we can practice again. Okay, so that's the start point. Proposition is the statement or is the assertion. That's another name. I'm not going to use the statement because it's really a confusion with the I will use sentences. Maybe proposition is the sentences whether could be true or false, not both. Okay, so proposition is the statement whether is true or false, not both. So that's the definition. Either is true or false, not both. Okay, so one following sentences that you see which are proposition, like Donald Trump is the president of the United States. So now it's false, right? But it's something that you can decide about whether it's true or false. It can't be both at the same time. So that's a proposition. 2 + 3 is 6. This is a proposition because it's false, but it's proposition. Right now you can decide about whether this is true or false. Okay, I'm going to add one example here for something which is a proposition. For every positive integer, n, there is there is a prime number larger than n. Okay? You guys maybe don't know this is a true or false, but it can't be both. Do you agree with me? I don't know whether it's true or false, but there is no way to be both. Either it's true or false. Yeah.
Agreed.
Okay, so that is what we call proposition. So let's look at the other equations. Examples I have in 2.13. It says the following sentence, like ouch. I can't decide whether ouch is true or false. What time is it? I can't decide whether what time is it is true or false. So that's not a proposition. Another example, x plus 4 equals 6. Is it a proposition or not?
Not.
Because
it's a question.
It's not. It can't be true or false.
so this is not a proposition because we don't know, because truth value of statements depends on x. So means if x is 2 is true, if x is something else is false. So that's the statement which is true and false at the same time. Whichever is true and false at the same time can't be a proposition. So proposition is the one that right away you can decide this is true or false. Okay? Make sense? Can we practice this? The first one, it says, I'm looking for your faces. You're here, sorry. So determine whether these statements are proposition. X plus 1 is 2. Yes or no?
No.
No.
No. For the same reason for x plus 6. So x is undefined or unknown. The only positive integers that divide 7 are 1 and 7. Proposition or not?
Yes.
Yes.
Okay, actually it's a true proposition, right? Peel me a grape.
No.
No.
Okay. 2 plus 5 is 19.
Yes.
Yes. But it's false.
Proposition.
That's a false. He's quarterback on our football team.
No.
No, unless we know who he is, right?
Yeah.
He is undefined. Because for someone might be true, for some other people might be wrong. So that is not propositions. That is not proposition, okay? Okay, for problems like A, or for problems like here that I have defined something in terms of the X, can I make it to be a proposition? Can I change it somehow to make it a proposition? This is one example. So think about, like, for x plus 1 equals 2, we have decided, we knew this is not a proposition because for some x's is true, for some x's is false. So it's both true and false. Then it says, let's add something to the statement. So let's add something to the statement and see whether it's a proposition or not. So what is the brand new statement? What's the brand new statement? This is defined like this. For some real number x, we have x plus 1 equals 2. Is this a proposition or not?
No.
Can you right away decide about, for
Yes.
some real number of the x, we have x plus 1 equals 2 is a true or false statement?
True.
Because?
Because
That condition for some
there is
reason.
an answer.
Because there exists one x, because there exists one x that makes that statement equals true. So it didn't say anything about what is the x, but it says there exists means for some real number of x, this x plus 1 equals 2 is working or is true, right? Let's compare with the next one. For all real numbers, we have x plus 1 equals 2. I'm not, regardless of being true or false, okay? So forget about whether it's true or false. So regardless of being true or false, the question is a proposition or not? The question is this a proposition or not? Can you right away decide about this is a true statement or this is a false statement?
It's false.
I think it's false.
The second one for sure is false, but it's a proposition.
Yes.
First one is true, and it's a proposition, right? So because there exists some x equals 1, that the statement it works, right? So that equality works for x equals 1. So when you say for some real number of the x, that x plus 1 equals 2 is true. So that is a proposition because it's a true proposition. There exists one x for that. There exists one solution for that statement. And same thing when it says for all x's is false because it doesn't work for all x's, but you can decide about whether it's true and false. Does it make sense? So even if something is not proposition, I could change it in somehow in a way to be a proposition, either a false proposition or true proposition, okay? And this kind of wording that I have used for changes is called quantifiers, okay? So soon in 2.6, we will learn about quantifiers. So there are some statements, there are some propositions that works only for one x. So we call it there exists some x or for some real numbers, but there are some statements that works for anything. So that's why it's called for all x's, that's true. So it's called quantifiers. As I said, 2.6 is covered that type of statements. Any question for this one? Any question for this one? So let's review. The way that you guys need to decide about something is proposition or is not. Something is proposition or not. So this is two different things that we have to say which one is true, which one is false, okay? First one, it says the statement is not a proposition if you can't decide about whether it's true or false. Second one, it says the statement is not a proposition if you don't know how to prove whether it's true or false. Which one do you agree with? Which one looks correct?
I
think
think
the
the
second
second
one-
statement.
Is
First
correct?
The second one is correct.
It's correct. So let me bring one example. You say the second one is correct. So the statement is not a proposition, if we don't know how to verify the truth value, okay? So my example says Earth is the only planet in the universe that contains life. So my first question, is this a proposition?
Yes.
Because
It could
it
only
is.
be true or false. Either it is or it isn't. So it's just a kind of like a binary answer.
Because it's making a claim.
okay, so you're making a claim which somehow, somewhere, someday is going to prove either is true or false. If you or me or anyone in this time doesn't know this is true or false, but still you guys agree this is a proposition. We don't
Yeah,
know.
this is a proposition.
This is a proposition, but right now I don't know whether it's true or false. But somebody, by this knowledge at this point, I don't know whether it's true or false, but someday with more technology, more knowledge, maybe it's proved to be wrong or it's proved to be true. So if I don't know right now, but there is only one answer, it can't be both true and false. Do you agree with me? So this Earth has, there's another planet has life. It can't be both true and false. Either it's true or false. I don't know right now, but maybe someday I will know, right? So let's read the statement one more time. Statement is not proposition if we do not know how to verify true or false. That's one of the statements. We don't know how to prove it's true or false, but someday, somehow, we will know false or true, right? It can't be both of them at the same time, right? So now, can you fix your answer out of these two statements that I wrote first in this lecture note? Which one is true, which one is false? A proposition, statement is not a proposition if we can't decide about true or false. Statement is not a proposition if we don't know how to verify whether it's true or false. So this statement is false because you don't know how to show. Maybe someone else knows. A statement is not a proposition if you don't know how to verify whether this is true or false. No, this is false. This is wrong, because at this point, I don't know how to prove Earth is the only one that has life, but in future, maybe somebody else knows. Okay, but still there exists only one single answer for this. Earth is the only one has the life. Either is true or false, but we don't know it right now. Okay, so if we do not know how to verify true or false, that has nothing to do with being proposition or not. Does it make sense or not? Do you agree with this example?
Yeah, that makes sense.
Okay.
Yeah.
So the first one is true, right? Something is not proposition if you can't decide whether it's true or false. But if you don't know, maybe somebody else knows. Okay, so that was my example. There's another example in your lecture note. This is just one popular, I will say, open problem for years, which was from 1742. It says, every even integer greater than 2 can be written as a sum of two prime numbers, but this is a claim. As you said, this is a claim. Somewhere, someday, somebody can prove is true or false. It can't be both, right? Either they successfully prove it or just disprove it. But as of now, is this a proposition or not?
Yes.
It is a proposition. Okay, so you figure out what's the difference, right? Proposition, not necessarily right now you have a solution for that to be a true or false, but either could be true or false, can't be at the same time true and false. Okay, so this statement, maybe someday somebody bring counter example and just say that's a false, or maybe somebody bring a proof and prove it, and that is actually for now is proving because there's no counter example for that. So that is a proposition. It cannot be true and false at the same time. So it's a proposition. Question, comment? Any question here? No? In order to show the propositions, we have different letters. So always we go by lower cases. So if you have a proposition, P, Q, or R is the propositions. But if we want to just show the sets, sets always is with the capital letter. So P, Q, R lowercase is going to be for proposition. If your proposition has variables, so as we know from algebra, X, Y, Z is the letters, still lowercase for the variables. Then for just what did I have over here? For propositions, you have only two possible cases. Okay, as we know, either is true or false. It can't be true and false at the same time. Either is true or false. It can't be true and false at the same time. I know you guys, when you're just doing the computer science, you might use the 0, 1. I'm okay with that notations also. So if your truth table coming with the 0 and 1, it's perfectly makes sense. So you can use the 0, 1. So 1 stands for true, 0 stands for the false. And that's fine if you use that notation. There are many operations that we want to learn on the, actually there are 6 of them that we want to learn on the propositions. One of them is negation. We all know what the negation means, right? So you negate anything, so it means you just go with the opposite one. So opposite of any proposition means negation. Notations are really varies from one to the other book. So some books use bar as negation, some books use this for the negation, some books use this for the negation. So there are even some, I think computer science use this dot for the negation. So there are different notation, whichever you use, I'm fine with that for that negation notation. As we know, for the truth table, if one statement is true, negation of that has to be false. If one statement is false, negation of that has to be true. Make sense by now? Do you want to add anything, guys? So can you please negate my statement? Can you please negate this statement?
X is a real number such that X does not equal 4?
Exactly, right? So X is a real number. X is a real number which X is not equal 4, okay? So let me just add some other examples. So if I call this one to be P, negation of P, as you said, X is a real number such that X is not equal 4. Okay. Q statement is 2 plus 5 equals 19. I try to use different letters with this different notation only just to practice to know all of them are okay. You can use either one you like. Negation of Q is 2 plus 5 not equal 19. Like R could be Donald Trump is the president. Sorry, I'm using this one because that's part of your book. Example. Okay. So then I have used the bar notation. I've used this notation. So I haven't used this one. But this is the other notation for negation. Make sense? Make sense? Any comment?
I have a question. What's is the Q where it says 2 plus 9 doesn't equal 19? Is that supposed to be like a squiggly, like the R? Or is that something different?
This one, right?
Yes. Okay, thank you. I just wanted to make sure.
Yeah, there are 3 different notations for this one. I mean, they are all the same. You can use either one you like. but you will see in your book all of these notations. You guys, how do you use it in your computer science? How do you put negation in your computer science?
Yeah, exclamation mark in front of the, like for not. So, and like if it was P, then you'd have like an exclamation mark in front, and then P would be like not P.
Yeah, Hamad put it in the chat.
Front, huh? So let's say P like this.
No, so it would be like P and then colon, and say you, like for the first example, you say X is a real number such that, and then X exclamation point equal sign 4.
Yeah, the way Kyle, his syntax put it in the chat, that's how it would look.
So you can keep this one, right? So I'm okay with any notations, okay? As long as it's true, it's true. So for your textbook, mostly using bar notation, but either one is fine, okay? So as long as we understand it's negation, so you can use the notation. Any comment for me? Thank you, Kyle, Hamid. So this is a quick reminder for you guys because you've seen these notations long time ago in very first level of the algebra. So if you're using the N, capital N notation with the little bar in handwriting, so you can put the little bar over here, or you can put the little bar over here. So this is going to be the set of all natural numbers or counting numbers. So which is 1, 2, 3, and all the way to the infinity. If you see the integers, is a Z letter, and that means you have positive and negative and 0. So you have dot, 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 and then you have -3, -2, -1, 0, 1, 2, and then 3, dot, dot, dot. That's a Z notation. This is a Z notation. They're all capital letter, okay? For quotient, so quotient is, if we want to write by handwriting, we put a little line over here. So it's the set of all numbers can be written in fraction or as fraction. So that's quotients as fraction. So that's a quotient. The set of real numbers, if you write the R but with the little bar beside, so that is the set of all real numbers, okay? If I want to use the notation, which you'll see soon, we have the set of irrational number, if you remember. So if you have a quotient, something not quotient is irrational. So this is irrational number. Anyone remember what's irrational? Can you give me one example of irrational? Pi, huh? E, right? You have a square root of like 3, whichever is not perfect square. Square root of 17. So whichever is not perfect square, and then pi and e, they are the list of irrational number. So whatever is not quotient or cannot be written as a fraction is going to be irrational. So that's a notation that you guys seen long time ago. The notation for the sets, as I mentioned shortly, it's going to be always capital letters. If you remember, I said for sets, always we use capital letters. If you want to say something is inside that or something is elements of that set, we use the lowercase. So for elements, always lowercase. For set, name of the sets is always capital letters, sorry. Then you have this notation. I don't know you guys seen or know or not. So this means belongs notation or in. So you can say B, lowercase b is in the set of B, or you can say lowercase b is belongs to the capital B or set of B. So that's a notation, is a curly E. Notation is like a curly E. I'm okay by now. Do you guys have anything to add? Any question? Okay. There are another notations. If you want to maybe just mention all real numbers, only the one that's a positive or only the one that's a negative, use the notation. You see, if you want to say you're having all positive real numbers, if you want to say all positive real numbers, you put the R for the real numbers, and the top or the power is the positive. So it says all positive numbers, which doesn't include 0. So that does not include 0. If you want to say everything except the 0, if you want to say everything except the 0, we just have a star notation. If you have everything non-zero, we have a star notation. So for example, you can have Z star. Z star means non-zero integers. R star means non-zero real numbers. So if I say Z negative, means negative integers. Obviously doesn't have 0, right? Because 0 is not positive or negative. Make sense? That's the notations. And again, this specifically, this is star notation is only for your book or only for this textbook. It's different, maybe star notation in other books they're using for different purposes. For your book, we are using this star notation for non-zeros, because there are many places that we don't want to divide by 0. We don't want to have undefined. That's putting the domain to be R star or non-zero numbers. So then for if you have any sets, which is called S, if you have any number lowercase k, so you can use the k times S. So what do I mean? Let's say your S is a set like just having 2, maybe 7 and 10 is the set of capital S. And maybe I want to say what is 3 times of S. So maybe it's nonsense as a calculus class if you can't 3 times a set, but here it's defined as a notation, means 3 times of 2 is 6, 3 times of 7 is 21, and 30. So that's what it says. So this is one contract here for this book. If you want to 3 times any element of a set, we can put a scalar multiplication on that set. That makes sense for this book. Okay.
Question.
Sure.
For the non-zero integers, can you show an example of like what that would look like? Like how would a non-zero look like? I've never heard of that before.
Non-zero integers, everything except 0. So it's going to be ... -3, -2, -1, then 1, 2, 3, so on. It has everything except 0. Same thing. Go ahead, sorry.
No, you're good. I was just saying my bad. Like, I feel kind of dumb asking that question.
No. That was a perfect. For sure, anyone has the same question that they don't dare to ask question. That was a good one. So for R star means everything except 0. So you can have all real numbers except 0.
Can you explain the R plus again? Like, what's the notation? You wrote negative integers, but like, what's the written notation that's next to it on the left-hand side?
For R, you mean, right?
Yeah.
So when we have R plus, means all real numbers which are positive. Everything which is positive, not 0, is R plus. That make sense or no?
Yeah, thank you for clearing that up.
Any other question? Yeah, that's another notation. Yeah, I like that notation. In calculus, we use that notation more. Yeah. So your book put the notation for R star. We have R maybe this way, or maybe the way that you said. That's another way to say. Makes sense. Something is correct, right? It's acceptable. So just one example here. Your Z is, what was it? All of the integers. So you have a -3, -2, -1, 0. Then you have 1, 2, and 3, ... So the question is 2 times of the Z. So which will be the set of basically even number, right? So ... you have a -6, 2 times of -2, 2 times of -1, 2 times of 0, 2 times of 1, and 4 and 6, and so on. So that's exactly the set of even numbers. Any comment for me for this one? Any question for me to this one? Okay. Before moving to a conjunction, disjunction, I want to give you a 2 minutes pause. If you guys want to stretch yourself, if you want to grab water or check your phone. So only 2 minutes pause, okay? Okay. Can I have one in the chat if everyone is here with me? Can I have number 1 typed in the chat if everyone is here with me? Thank you. Great, thank you so much. So for any relations, right? So any connections between this, if you want to get any connection between propositions. So this is just remind us, there are 2 types of operations between what we call numbers, right? So you can have addition, subtraction, and product and division, which are binary operations. What does it mean? You need 2 numbers to add, you need 2 numbers to subtract, you need 2 numbers to multiply, you need 2 numbers to divide. So those are binary operations. And we do have unary operations. So unary operation is like opposite. So if you have 2, then you have negative of 2. So you have 5, you have negative of 5. So those are unary operations. So operation that works with only one number is unary, like negation, like negative or opposite. And then if you need 2 numbers to make, so that would be binary operation. So as of now, you guys know what's the binary operation for a statement, right? So unary operation for a statement is negation. Unary operation for statements, for propositions, is negation. We want to practice how you can have compound statement. You want to practice how you can have binary operations for any this statement or propositions that we have started. Okay, so how many do I have? Binary operation 1, 2, 3, 4, 5. I have 5 binary operations, or you can have 5 types of compound statements for the propositions. Okay, so this 2.2 is only only 2 of them, which is disjunction and conjunction. Again, you've seen what we call conjunction as disjunction because you know what is and, you know what is or. So even in other courses that you are practicing right now, you know what is and in maybe circuits. I don't know which kind of course you are practicing, or we just have different names for that. For and, we call it conjunction. For or, we call it disjunction. So if you have the statement of the P to be it's raining, statement of the Q it's cold, so you have P and Q, so it's raining and it's cold. So that's conjunction. So this is called conjunction. Notation wise, we're using this notation. Again, you guys might use different notation in different courses. And then a disjunction is or. So we use the V shape exactly for disjunction. So it's raining or it's cold. So and conjunction or disjunction. For truth table, I think you guys can help me to fill out my truth table. So if you have a P and then Q, and you want to make P and Q, which one is true? True is?
True.
True, false is?
False.
False, true?
False.
False, false?
False.
So all of them false, right? So then for and statement, or for what we call conjunction statement, it's right over here. It says the conjunction statement is true if P and Q both are true. If P and Q both are true is true, otherwise is false. So only if true is true, the rest of them is false. So for and statement or conjunction, only true is true, the rest of them is false. And similarly for the disjunction, if you have it's raining or it's cold, if it's raining or it's cold, so for either being raining and cold, you still are true. Even if it's raining but not cold, still you are true. If it's not raining and it's cold, still you are true. The only way that for or statement you will be false is when both of the statements are false. So one more time, the false is false. For disjunction, everything else is true. And this is how it is explained over here. If one of the statement is true, is going to be true, otherwise is going to be false. Any question here? Does it make sense? Any question here? Okay, so let's practice with the examples. Okay, practice with the examples. So first one, it says write X and Y are rational as conjunction. Write as conjunction statement and then write the math notations for that. So P statement, X is rational. Q statement, Y is rational. So your statement says X is rational and Y is rational. Do you agree? So when we say X and Y are rational, means X is rational and Y is rational. So it's going to be P and Q. Is going to be P and Q. Make sense? Any question with this one?
So conjunction, or I think that's what they're called, right? Conjunctions are ands and disjunctions are ors.
Mhm,
Okay, thank you.
exactly. You're welcome. So next example, determine the truth value of this statement. Determine the truth value of this statement. So first is New York is the largest state. The second, New York City is the capital for the New York, okay? So then what do I have over here?
False.
False, huh? Which one is false?
The first one.
The P.
Is the second one true?
Yes. Wait, is it?
Does it matter?
No.
Okay, it doesn't matter. That's what it's explaining right over here. It says in general, if you're talking about and statement or conjunction statement, so as soon as you see one false, you don't need to just worry about the rest of things, right? Because false by anything is going to be false in and or conjunction statement. So this method that we don't care about the second one, or you don't care about the rest of terms because you're false and anything else is going to be false, is called short circuit evaluation. Short circuit evaluation is when you're having conjunction and one of the statement is false. So you're sure it's false, don't worry about the rest. By the way, is really New York City the capital for the New York or not? No, it's not, right? So that one also is false. Okay. So few numbers. I want to use that short circuit evaluation, right? So because I have and statement. So because I have and statement, is there any of these two false? Is there any of these two statements false?
The second one is false. Sorry, A is false.
I'm going to call this one P, then Q, then you can know which one is it. So
Q is
RAT
false.
25, Q is false, huh? Is 5. So then RAT 30 bigger than 7 is for sure false, okay? So regardless of the P, the conjunction statement is false. So regardless of whatever is the truth value for the first one, since the second one is false, is false. Okay. And similarly, you can just have the same strategy for the conjunction. As soon as one of them is true, right? As soon as one of them is true, right? So do I have any of these two to be true? The first one is, yeah, I should call P and Q. You're right. So this is a P, this is a Q, huh? This is a P and this is a Q. So RAD 30 is bigger than 5, and that's true. So as soon as one of them is true, so then it's going to be true. But this is actually true or true. But I'm going to still use the same argument. Regardless of truth value of Q, the disjunction statement is true. Because true of anything with the disjunction is going to be true. Fine. Question here. How do I write x is between 0 and 1 in logical? Is it disjunction or conjunction? Is this disjunction or conjunction?
Conjunction.
Conjunction, so means x is bigger than 0 and x is less than equals 1. So what's the negation of that? What is the negation of this statement?
0 is greater than and or equal to 1. I'm sorry, x, which is greater than or equal to 1.
Okay. How about the notation between them? Is it and or or?
And
Okay, so let's look at to the algebra part. This is 0 and 1, right? Your first statement, which is the P statement, it's claiming x is sitting between 0 and 1. X is sitting between 0 and 1, so that is the P statement. Your Q statement is going to say, sorry, your P not statement is going to say your numbers are sitting over here. Is it and or or?
Or
Would be or.
It is or. Because if it's x not between 0 and 1, either has to be less than 0 or bigger than 1. Does it make sense in calculus or algebra? If x is not between 0 and 1, either is less than 0 or bigger than 1. So that is disjunction. This is really interesting, right? Is switching. We have actually a theorem for that. This is a name of a theorem. If you have P and Q and you negate P and Q, so then it will be first negate. Oops, sorry. It's a negation of first one or negation of second one. So this is actually a theorem. Anyone knows what's the name of this theorem? Have you ever seen it? If not, you'll see it here soon. You will see De Morgan's theorem. De Morgan's theorem is the one that says whenever you negate notation, disjunction will be conjunction, conjunction will be disjunction. So it switch always. Anyone wants to add any question, comment? No? So let's practice the truth table. Let's practice the truth table. First of all, how many rows do I need in my truth table?
or
Because
we have to do P, Q, and then the negation of Q, and then the P and the negation of Q.
so you have to do P, you have to do Q, you have to do negation of Q. That shows the order of operation, right? So order of operation, negation of Q, or your Q bar says you go with the negation first and then conjunction. So you go with the negation first and then you go by conjunction, okay? I don't know why I'm using both notation, once here, okay? So that's the number of columns, but I ask you about the number of rows. Number of rows in truth table equals 2 to the power of number of statements. How many statements do I have? How many statements do I have? I have two statements of P and Q. I have two statements of P and Q. So I have 2 to the power of 2, 4 rows. I do have 4 rows in my table, right? 2 to the power of 2 is 2 statements of P and Q. So I have 4 rows. So is it true, true, false, false? Is it true, false, true, false? So please start. I know you guys might use the 0 and 1. As I said, I won't have any problem if you use the 0 and 1. So you can use the 0 and 1. But if you're using either 0 and 1 or true and false, you must write it in this order, okay? It's not wrong if you write it in the other way. So you see what I'm talking about. So you can just write 1, 1, and then 0, 0. And it will be really disaster if you go the other way, 0, 0, and then 1, 1. Don't do that one with me, okay? It's hard to check. It's not wrong, but it's hard to check. So if you go by 0, 1, it's perfect. If you go by true, false, you must go by this order. I mean, start with the true. So 2 trues and then 2 false, 1 true, false, 1 true, false, okay? So the negation of this one is going to be false. Negation is true. Negation is false. Negation is true. And that's the and between these two columns. That's the and between these two columns, okay? And I'll find my true false first, sorry. If I have any true, true, oh, it's right over here. If I have any true, true, it's true, otherwise it's false. So that's a truth value. Do I have anyone haven't seen this kind of table? Never ever?
I've seen it before. The true, true, false, false. I've seen it.
Mm. Okay. Can we try one more? So table, this 1, 2, 3, and 4 lines, because still I have 2. Still I do have 2 statements of P and Q. So 1 column for P, 1 column for Q, 1 column for negation of P, 1 column for negation of Q, 1 column for inside the parentheses, 1 column for outside the parentheses. So you see the order of operation still is like algebra. Inside the parentheses is first. Negation is first and then inside the parentheses. So negation of Q. So you have negation of P or negation of Q. Then the last one is whatever is the statement. Anyone has any problem with this way of writing? Any of steps is missing for you guys? Or you have any question about any of these steps? No? Filling out? True, then true, false, then false, 2 by 2. True, false, true, false. So then I have true, true. Oh, sorry. True is false, false, true, true. That's a negation of the P. And this is a false and true. This is a false and true. So if you're having or you're looking for something to be false, false. Between these two, this is only false, false. The rest of them is true. And if you're looking for, again, or, which is between this column and this column. So you're looking for any false, false. There is none. Are you okay? Do you agree with me? The statement which is always true is called tautology. Tautology. So this is a tautology, actually. This statement which is always false is called a contradiction. The good example for tautology is P or negation of P is always true. P and negation of P is always wrong. So this is always true, this is always false. Those are good examples. This is also one tautology. This is also one tautology.
So no matter what, if we were to do like a true false table, P is always going to be true, true, false, false.
Mhm.
Okay.
Unless you have more statements. Don't forget, this is for two statements. So if you have three statements, P, then Q and R, so it's going to be true, 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 false, 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 then true, true, false, false, true, true, false, false, then true, false, then true, false, then true, false, then true, false, okay? Since you have three statements, you have 8 rows. Does it make sense how it's changing in a power of 2?
Yes.
Or you want to distribute? Not really. No. So Hamid, if you want to do in that way, because you can't distribute with the or, you can't distribute in the or. I don't know, it's too hard how you guys writing on this notation. So you have to just really, if you talk is better than typing. But anyway, so this is going to be or. So distribution is for different notation. So if you have or and, if you have and or, you distribute it. But if you have this one, you can use associative property. So which means you, instead of keeping P and Q together, you can just put P bar and P bar together. So then if you keep the Q here and you move the P bar and P, since they are the same notation is correct. This is associative property. So then you have a Q bar, since P bar and P, yeah, you got it, huh? It's true, so then it's true. So this is another type of method, right? So this is just when you use the properties to prove its tautology. This is when you use the truth table to show this is tautology. Either one is fine. Either one is perfect. But distribution is with different notation. If you have the same notation, you use associative property. You'll see it soon, okay? Sorry, guys, I passed the time. I'm sorry. Should I add anything, guys? If you have any if you have any question